So last section we're going to look at this week is 6-5. Okay, the plan is to split it into 2 days, but if we don't, the second part has more in it than the first. So if we don't quite finish the second part tomorrow, we don't have to rush through it. We'll just finish it on Thursday. Not a big deal. So what we're going to be looking at in this section is completely different from 6-4. Okay, we're going to get away from graphing, and we're going to look at right triangles. Okay, what we're really going to be doing is figuring out ultimately how long each side is in a triangle and how big each angle is. That's going to be the goal. All right, so first let's just talk about what a right triangle is. Can someone remind me what makes a right triangle a right triangle? What's special about it? Francesca?
90-degree angle.
Yep, it has a 90-degree angle. So it's a triangle with a 90-degree angle, which that's why we call it a right triangle, because that's a right angle. And what do you call the side in a right triangle that's across from the 90? It's the longest side. Jake?
Hypotenuse.
Yep, the hypotenuse. And what about the two shorter sides? Anyone remember what you call those? Yep.
Legs.
The legs. Good. So the side opposite the right angle is the hypotenuse. We just said that. The other two sides are the legs. And here's a sketch of everything we just said. When we have to label the sides, because we don't know what they are, we are going to use the letters A, B, and C. A and B can represent either one of the two legs, but I want you to make sure you use C for the hypotenuse. Now this angle in the lower right and this one up at the top, these are both going to be what we call acute angles. I think we already defined that earlier in chapter 6. An acute angle is an angle that's between 0 and 90. But can anybody tell me why this angle has to be between 0 and 90? Why couldn't it be bigger than 90? Yeah.
It would be an obtuse angle if it was.
Okay, what would be wrong with that? So triangles can't have obtuse angles?
They can, they just wouldn't be acute angles if they did.
So they can, but what did you say?
Like, they can be obtuse, but like it wouldn't be classified as an acute angle if it was obtuse. Never mind. Skip over what I said.
So why does this have to be acute though? Why can't it be obtuse? So that's my question. Why can't it be an obtuse angle instead of an acute angle? What would happen if it was bigger than 90? Yeah?
So the angle is bigger than 90, then wouldn't the 90-degree angle just like go away? Wouldn't it not be a right triangle anymore?
Why? Why would the right angle have to go away?
Because then you would have a large angle and then you have two smaller angles. There are two angles less than 90 and one angle bigger than 90.
And is there anything that we know about angles in a triangle? Something that's supposed to happen? They have to add up to 180. So if you have a right triangle, you've already used up 90. That means the other two have to add up to 90 between them. So if these have to add up to 90, they each have to be smaller than 90. They couldn't have one of them equal to 90, because then you'd have a shape like this. That wouldn't be a triangle. So the other angle has to be a little bit smaller than 90, or it has to be acute, okay, to make a triangle. There's also a theorem that we can use that relates all the sides in a right triangle. Does anybody remember the name of a theorem you can use if you know two of the sides and you could find the third one? Yeah?
Pythagorean Theorem.
Yeah, yes, Pythagorean Theorem. So Pythagorean Theorem is pretty common in geometry, and it involves all the sides. Does anybody remember what that theorem, well, what the formula is, and then I'd like you to explain what that formula means. Yep.
A squared plus b squared equals c squared.
Okay, and what do you mean when you say a squared plus b squared equals c squared?
The number, the length of a and b squared is equal to the length of c squared.
And what is a and what is b?
The two legs.
The two legs. Okay, so that's the whole key. In the Pythagorean theorem, you take one of the legs and square it. You take the other leg and square it. Add them together, and that's equal to the hypotenuse squared. Doesn't really matter what you call them. We're going to use a, b, and c. But that's the idea behind it. Squaring the legs and the hypotenuse. Right, any question on that theorem? Keep in mind that that's a theorem that only applies to right triangles. So when we have problems like this eventually, that is not a problem you can use Pythagorean theorem in. There's no 90-degree angle. Okay. You're not going to have that yet. So we're going to take a look at the 6 trig functions. We've already defined them before. We looked at them when we did unit circle. We looked at them again when we did graphing. But now we're going to define them. Instead of using like sine equals y, cosine equals x, and tangent is y over x, that was unit circle. We're going to define them using the words opposite, adjacent, and hypotenuse. So let me give you the definitions, and then I'll explain. Well, I think everybody knows what hypotenuse means. But then I'll explain what opposite and adjacent mean. These are all lengths. Okay. When I say opposite, I mean length of the opposite. And when I say hypotenuse, I mean length of the hypotenuse. So sine is defined to be the length of the opposite side in the triangle divided by the length of the hypotenuse. Cosine is defined to be the length of the adjacent side in the triangle divided by the hypotenuse. And tangent is defined to be the length of the opposite side over the length of the adjacent side. And the way some people remember this, if it's helpful, great. If it's not, then, well, don't use this. Sine is opposite over hypotenuse. Sine is OH. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. So cosine, adjacent over hypotenuse. And then tangent is opposite over adjacent. T-O-A. T-O-A. Has anyone seen that or learned that before? Sakatella? That's one way you can try to remember the different trig functions. One year I asked somebody what this trick was to remember it, and they said Sacagawea. Nope, not quite. Sacagawea doesn't help, but Sakatoa does. So if you remember Sakatoa, you can kind of remember which ones are which. Now, we have 3 on the left, and then we have 3 on the right. And we always do something with the one on the left to get the one on the right. In fact, we just had to do it in the homework when we had to graph. What do you do with the one on the left to get the one on the right? Yeah.
Divided by 1. Like one on top.
But yeah, so in doing that really does what to a fraction? Takes your fraction and, yeah, it flips it. Right? So it takes it and it flips it. So for cosecant, we're going to have hypotenuse over opposite. How about, Abigail, what would my secant be?
I'm sorry, what?
What would my secant be?
Hypotenuse over adjacent.
Yep, hypotenuse over adjacent. And Jeff, what about my cotangent?
Adjacent over the opposite.
Adjacent over opposite. So now, again, I think everybody knows what hypotenuse means, right? It's the side across from the 90, but what do opposite and adjacent mean? Like, how do you figure out if you're looking at a triangle, oh, this is the opposite and this is the adjacent. How do you know that? Well, opposite and adjacent are what we call relative terms. Okay, and the way I try to explain it is they're kind of like left and right. Left and right are relative to where you are. So for me, left and right is different than for you, because you're facing a different way. And that's how opposite and adjacent are. So how do you figure out which way you're facing in a triangle? Well, like this. You have to pick an angle that's not the 90. Usually that's not a choice you can make. They'll pick it for you. Let's say we pick this angle down here. That is my perspective. So imagine you're standing at theta. Everything is now from the perspective of theta. So opposite is the side that is farthest away. It's the side that if you erased it, it has nothing to do with this angle at all. This angle is still right there. Okay. Adjacent is the side that's next to your angle. You might think, well, wait, there's two. Well, it's the side that's not the hypotenuse. So this is the hypotenuse. This is the adjacent. It's the side that's next to your angle, but not the hypotenuse. Now, adjacent is the side that if you erase it, you just wiped out your angle. You don't have an angle there anymore. The bottom of the angle is now open. So you lost one side of your angle. And if you take the same triangle, and instead of referencing everything from the lower right, say we reference everything from the top. Well, the hypotenuse is still the same. In this room, that would kind of be like asking you which way is up. It doesn't matter if you face this way or you face the door. Up is still the same way. Okay, that's kind of like hypotenuse. It stays the same. But if you face a different way, the opposite and adjacent switch. Opposite is the side that's furthest away from the reference point of your angle. Adjacent is the side that's next to your angle, but not the hypotenuse. Right, so when I say opposite and adjacent, that's what I mean. Questions on that? So, if we have two right triangles, and the angles are all the same, does anybody remember what you can call those triangles? Two triangles, and the angles are all the same. Yeah? So, let me explain a little different. The angles aren't necessarily all the same within the triangle, but if you look at triangle 1 and triangle 2, all the corresponding angles are matching. So like the first angle in this triangle matches the first angle in this triangle, whatever it is. Does anybody remember what you'd call that if you have two triangular shapes and the angles match in both of them? The angles are congruent, I should say it that way. Well, if the angles are congruent, does that mean that the triangles are identical? Jake?
Not necessarily. They don't have to be.
They don't have to be equal, right? If I said to you, I have an equilateral triangle, and I have another equilateral triangle, does it mean they're exactly the same size? It means all the angles are 60, okay, but it doesn't necessarily mean they're the same exact size triangle. So what do we call two shapes that have the same angles, but they could be different sizes? Remember? Begins with an S. Yeah?
Symmetrical.
It was a good guess. Not symmetrical. That was a good guess. Anyone have another guess? Two shapes that one could be a larger or smaller version of the other? Yep.
Similar.
Similar. Okay. And what I want you to understand is that when you do trig, the size of the triangle doesn't matter. Let's say you wanted to find the cosine of a 30-degree angle. And you asked me, well, how big is the triangle? I would say it doesn't matter. You could have a triangle with a really tiny 30-degree angle, or you could have a triangle that's miles wide on each side, and it has a 30-degree angle. The cosine of 30 degrees is always going to be the cosine of 30 degrees. Doesn't matter how big or small of a triangle it's in. Let me show you. Okay, so trig functions always have the same value for a given angle. Let's look at this example. These are two 30, 60, 90 right triangles. And the sides are properly scaled. So these are to scale pictures. Let's find the sine of 30 degrees in the left triangle. What did we say sine was? It's the length of what over the length of what? Okay?
Opposite over hypotenuse.
Opposite over hypotenuse. So what would the sine of 30 be in a small triangle?
1 over 2.
1 over 2. Now, let's look at this triangle off to the right. Did anybody see what did I do to this small triangle to get the bigger triangle? Anybody see what the scale factor is? Yeah. 2. I scaled everything up by a factor of 2. So I doubled every side, and that's how I got this one. Well, let's find the sine of 30 in this one and see what happens. Again, opposite over hypotenuse. Chris, what's the side opposite the 30 degree in this problem?
2.
2. And what's the hypotenuse?
4.
And what does that reduce to?
1/2.
1/2. So the point is, even though this is a bigger triangle, when you're finding a trig function of an angle, it has nothing to do with the scale of the triangle. Big, small, doesn't matter. And that's why when you go on the calculator and you type in something like, let's just change to degrees. That's why when I type in sine 30 degrees, it can tell me the answer is 1/2. I didn't tell the calculator how big of a triangle I was talking about. All I did was tell the calculator the angle. That's all it needs to know. It doesn't need to know how big the triangle is, because it doesn't matter. Okay. Any question on that? All right, so now we're going to look at a problem like this in a second. Right? But first, before you write it down, I kind of want to explain how to do it, or maybe see if you know how to do it. I'm going to tell you one of the 6 trig functions, and I'm going to want you to find the other 5. If I tell you that the sine is 5 over 6, what have I really told you? Yeah?
The opposite of theta is 5, and the adjacent to theta is 6.
So I agree, the opposite side from theta is 5, and the what is 6?
Adjacent.
That would be if I told you the
Hypotenuse.
tangent.
Hypotenuse.
Hypotenuse. So I've really given you 2 of the sides in a triangle. Well, to find the other trig functions, you need the third side. If you know 2 of the sides, how can you get the third one? Ashley?
Pythagorean theorem.
You can use the Pythagorean theorem. And we're going to write that down right now. That's how you do it. So to find the 6 trig functions, if I give you one of them, take whichever one I give you and use the information that I give you to label two sides of a triangle. You're either going to know the opposite and the hypotenuse, the adjacent and the hypotenuse, or the opposite and the adjacent. You'll know one of those three combinations. Once you label the two sides that you know, use the Pythagorean Theorem to find the side that you don't know. Find the third side. And then once you have the third side, you can figure out any trig function you want. It's up to you. You don't have to write that last part. That's what the third side allows you to do. Once you have the third side, you have everything, and you can find all 6 trig functions. Now, again, just to be clear about what we're doing, we are finding the trig functions of the angles. We are not finding the angle. We could, but we're not. Okay, that'll be tomorrow. You're finding the trig function of the angle, not the angle itself. So when you're done, all your answers are going to be fractions, like opposite over hypotenuse or adjacent over hypotenuse and so on. We'll practice all 6, but if it was a problem on a test, I would probably only ask you for 1 trig function per problem. We'll try all 6. Okay, so it says let theta be an acute angle where the sine of theta equals 5, 6. Now, when you draw a triangle, you can put the theta wherever you want. And you can draw your right triangle however you want. If you want to have it face this way, that's not normally how I do it, but we could do it that way, that's fine. And pick where you want to put theta. Let's put it down here. Up to this point, you can't really go wrong. Now you have to start putting things in the right spot. So, Casey, what side is the 5 again? That's opposite. And Eli, what side is the 6?
The bottom.
Or
the top.
Can you give me the word that describes it?
The adjacent.
No, adjacent would be the base.
The hypotenuse.
Hypotenuse. Okay, so 5 over 6. Now we need the third side, okay, in order to find all the trig functions. So Francesco, what could I call the third side for now until I get a number for it?
X.
Yeah, we could call it X. Could also call it A or B if you wanted to. And let's set up Pythagorean Theorem and solve for X. So Ethan, can you help me set up my formula to solve for X?
5 squared plus x squared equals 6 squared.
There we go. 5 squared plus x squared equals 6 squared. And Chris, 5 squared gives me 25. And Tyler, 6 squared?
36.
36. Okay, and Ashley, what would be my next step?
To subtract 25 from 36.
Subtract 25 from each side. That's going to give me 11. And Bailey, my last step?
Take the square root of each side.
Yep, take the square root. And when you're doing a problem that has these directions, we're not going to use decimals. And the directions on the test will say leave as an exact answer. So square root of 11 is exactly how we're going to leave it. Okay, now we know every side. Let's make a chart for all 6 trig functions. Sine. Well, we already know that one, 5/6. How about my cosine? Jake, what's my cosine going to be?
Square root of 11 over 6.
Yep, and we're not going to do anything with it. We just leave it. Could I do something with that to get rid of cosine and get theta by itself? Yes, I could. I can tell you exactly how big that angle is. That's tomorrow. All right, so we got the cosine. I also want the tangent. All right, what would, Sarah, what would my tangent be?
5 over square root of 11.
All right, 5 over square root of 11. And any thoughts about 5 over the square root of 11? Yep.
There can't be a square root in the bottom.
Yeah, we can't leave the square root in the bottom, so we need to fix that. How do you fix having a square root in the bottom? What do you have to multiply by? Francesca?
You multiply it by the square root.
By what?
The square root, so that you multiply.
Yep, multiply the top and the bottom by the square root. So the top becomes 5 times the square root of 11, and the bottom becomes the square root of 11 times the square root of 11, which is 11. Okay, so those are the first three. Now, what do we do? Because we don't really have to do too much work. Once we have the 3 on the left, what do you do with each one of them to get the 3 on the right? Yeah, just flip them. So cosecant. That one's pretty easy because we don't have to deal with a square root. 6/5. How about secant? Anyone think they can tell me what the secant would be after you flip it and you fix it? Yeah, Chris?
6 times the square root of 11 over 11.
Good. 6 square root of 11 over 11. And lastly, for the cotangent, you have a choice. You could either flip what's circled in red, or you could flip what's circled in black. There's an equal sign between them. They're the same thing. But which one do you think would be better to flip? Eli?
The one circled in red,
Why?
because you won't have a square root on the bottom.
Yep, you flip the one that's in red and you're done. You flip the one that's in black, now you got a root in the bottom again, you got to fix it all over again. So let's flip the first one. Square root of 11 over 5. Nowhere in that problem did we actually solve for how big the angle is. That wasn't the goal. The goal was to find the trig functions of the angle. And there are 6 of them. Okay, any questions on that? All right. The next one was the same as this. Does anyone feel they'd like to see another one like that? The only difference in this one is it actually came out to nice sides. So I'm not going to go through it, but Pythagorean Theorem would give you 13. And then no square roots in this problem, so that's a little easier. All right, so let's see if we can find the 6 trig functions of 45 degrees. Now, let me erase these for a second. What did I say earlier? If you're trying to find a trig function of an angle, does it matter what size triangle you use? No. So if you need to find the 6 trig functions of 45, all you need to do is draw a 45, 45, 90 triangle. It can be absolutely any size you want it to be. It just has to follow the rules of a 45, 45, 90 triangle. What type of triangle is that when you have 2 angles that are the same? Remember? Yep.
Isosceles.
Isosceles. So if you have two angles that are the same, you have two sides that are the same. The two legs in a 45, 45, 90 triangle are always the same. So pick any number you want for the leg. Just make the other leg the same. That's all you have to do. I think the easiest numbers to use would be, let's make this a 1 and a 1. If you wanted to make it a 5 and a 5, sure. Just make them the same. And now, if you use Pythagorean Theorem, what would the hypotenuse have to be? Tyler?
1.
Well, if they were 1, 1, and 1, that would make it equilateral. Yep.
Square root of 2.
Square root of 2. Yep. And now from here, it's just like the last problem. The only difference this time is you weren't given any sides to start with. You had to figure out what you wanted your sides to be. Right. So let's do sine of 45. How about Abigail? Can you tell me what the sine of 45 is? Just say it again. 1 over the square root of 2. Doesn't matter which 45 you use. If you say, well, you said you should always pick which angle you're going to use, pick either one of them. They're the same. Use this one. You're not sure? Use that one. So opposite over hypotenuse. It is going to be 1 over the square root of 2, but I need to fix that. And that's what you get when you fix it. Jack, how about the cosine of 45?
1 over the square root of 2.
And it's the same thing, 1 over the square root of 2. And the tangent, Casey, what's the tangent of 45? 1. And Eli, to get the other 3, what would I do with each of those?
Flip them.
Just flip them. All right, so when we flip those, we're going to get square root of 2. Or if you don't want to think of it that way, think of it the way I wrote it on the board, hypotenuse over opposite, square root of 2 over 1. Secant, same thing. And whenever you have a trig function that comes out to 1, its reciprocal is also 1. All right, so those are the 6 trig functions of 45 degrees. Any questions on that one? All right, 1, 2. What's this? Okay. Now, let's look at this one for a second. This one is asking us to find the 6 trig functions of 30 and 60. And the hint that they're going to give us is use an equilateral triangle. Because what are all the angles in an equilateral triangle? Yeah.
Equal.
And that makes them all what number?
Same.
So what number would they be though? I agree. They are all the same, but they all have to be a certain number. Like, could they all be 5, 5, and 5 for the angles?
Well, wouldn't the angles have to add up to 180?
Yes.
But all of them would be 60.
All of them would be 60. Okay, so if you think about trying to figure out this problem using an equilateral triangle, that helps a lot. Now, if you draw a line right down the middle, you've just separated that into 2 congruent triangles. So what does that mean? That angle is right there. Yeah,
30 degrees.
that's a 30-degree angle, because you split the angle in half. So that's a 30, that's a 60, that's a 90. Now, well, we know in an equilateral triangle, all the sides are the same. It doesn't matter what size equilateral triangle you use. 1,000, 1,000, and 1,000. I mean, those would be big numbers, but you could. But if you look at this bottom side, how do you think this part in red compares to that part in green? Yep.
It's the same.
It's the same, right? They're each going to be the same. So can anybody think of a number we could let each side in the equilateral triangle be? So that we could have a number here and a number here that's the same, and when you add them up, you get the total length of that side. Anybody think of a number that we could let this entire side be? I mean, it could be any number, but keep in mind that this part and this part have to be the same. So I'd like to avoid a number with decimals if I could. Yep.
2.
2 would be a good number, because that's going to be half of it, or 1. I mean, if you did 3, that would have been fine, but then you would have made the other side 1.5. So look at what we know now. We just created that side to be 1. How long is that side in red? Yeah, it's got to be 2, because that's an equilateral triangle. And now all we need is the third side. And if you use Pythagorean Theorem, it would come out to square root of 3. Yep, square root of 3. So the only extra step we had to think about a little bit is, how should we label these sides? Right? And we have a lot of freedom, and that's what confuses people sometimes. I'm just not even sure where to start. This is the diagram that I would always use right here, if you have to do the trig functions of a 30, 60, 90 right triangle. Okay, now you have the diagram. And you could do opposite over hypotenuse, adjacent over hypotenuse, whatever you want to do. In fact, it might be the same diagram, 1, 2, square root of 3, that I had right here. Yep, 1, 2, square root of 3, same problem. Just turn it on its side. All right, so we've already gone through some of the trig functions in that other problem I just showed you. Not all of them. But is there any trig function here anyone would like me to do? Sine, cosine, any of them? For the 60 or for the 30?
Would you ask like which angle you would want it from?
I would have to tell you which angle I want it from, because that makes a difference. So if I say do it from the 30, then the 1 is the opposite, and the square root of 3 is the adjacent. If I tell you to do it from the 60, then what I just said switches. Yep. In this case, they asked for both. All right, so last thing. Remember that if two angles add up to 90, that's called complementary. And I think we already kind of answered this. But if you look at this triangle, why are angles 1 and 2 always going to be complementary? They have to be. Yeah.
Does the triangle have to add up to 180 and the right angle's already taken up 90?
Exactly.
Or does it add up to 90?
Yeah. So all the angles have to add up to 180. The right angle is already 90. So the other two have to add up to 90 together. You make two things together add up to 90. That's called complementary. All right, so now what I want to do is I want to show you the diagram that we're going to use when we have to draw a triangle. and we don't know anything. We don't know any of the sides, we don't know any of the angles. Well, we already have letters I taught you for the sides, A, B, C. So we're going to stick with those letters. But when we don't know an angle, generally we use a Greek letter. Now, our book doesn't do it that way. And I think it's confusing. Because let's say you do something like our book does, which uses capital letters for angles and lowercase letters for sides. And you ask me, how do you figure out B? I'd have to be like, well, which B do you mean? The capital B or the lowercase b? Which B are we talking about? Right. The other thing that can be confusing is depending on the capital letter you choose, some capital and lowercase letters look identical. Like O, that'd be an awful letter to use for several reasons. But a capital O and a lowercase o could look the same unless you have other letters around to see the size difference. It's too confusing. So to make it easier, English letters will always represent sides. Greek letters represent angles. Anybody remember the name of that Greek letter? Yeah.
Alpha.
Alpha. First letter in the Greek alphabet goes with the first letter in the English alphabet. Always put A opposite alpha. And we're always going to put B opposite. Anybody remember that one? Yep.
Beta.
Beta. B goes opposite beta. This angle, you never have to give a name to. It's the 90. A from alpha, B across from beta, and C is your hypotenuse. All right, so let's find something in this picture. Okay, it's not going to be numeric. There's no numbers in this picture. Let's do the sine of alpha. All right, so remember, sine is opposite over hypotenuse. How about Francesco? What side is opposite from alpha? Alpha. So beta is an angle. We're looking for a side.
So then, let's see.
C is hypotenuse, because that's across from a 90. Opposite and hypotenuse have to be one of the legs.
I'm confused.
So opposite is the side that's farthest away from your angle.
Furthest away from alpha?
Yes, alpha is the angle that we're referencing.
Wouldn't it be the A?
A. Yep. So sine of alpha is opposite over. And Ethan, what's my hypotenuse?
C.
C. Okay, so the sine of alpha is A over C. Now, I want to do a different problem, but I'm going to make it up based on the one I just did. Instead of sine, I'm going to put the word co in front of it. So now that becomes cosine. And instead of alpha, I'm going to use the angle that's complementary to alpha. Remember, we just said the two angles, angles 1 and 2, are complementary always. So the complement to alpha is beta. So that's a very special problem I just made up. I put the word co in front of sine, and now I'm using the complement of this angle, which is beta. Cosine. Chris, what's our definition for cosine?
Is the adjacent over the hypotenuse.
Adjacent over hypotenuse. And Ashley, what side is adjacent to beta?
B.
No, B is opposite beta. It's farthest away.
C.
No, C is hypotenuse. C is always, anything across from a 90 is always a hypotenuse.
Then A is the only other option.
Which one?
A.
A, yeah. A, remember, adjacent means next to. So A is right next to beta. So adjacent is A. And Bailey, what's the hypotenuse? C. Notice the sine of alpha and the cosine of beta came out exactly the same. Let's do one more. Tangent of alpha. And in the other problem I'm going to make up, I'm going to put the word co in front of that. And I'm going to use the angle that's complementary to alpha. Beta. Okay, so tangent. Jake, what's the definition of tangent?
Opposite over adjacent.
Yep. And what's opposite alpha?
A.
A. And what's adjacent to alpha?
B.
B. All right. So tangent of alpha is A divided by B. Let's look at the next one. Cotangent of beta. Cotangent is adjacent over opposite. So Sarah, what side is adjacent to beta? A. A is right next to it. And Abigail, what side is opposite beta? B. Notice again, these two came out exactly the same. And that will always happen if you follow the pattern that I've been doing. Putting the word co in front of that one, and putting the complement of that one. When you put co in front of a trig function, that's called a cofunction. There's three pairs of cofunctions. That's one. Sine, cosine, tangent, cotangent. That's two. Secant, cosecant. That's three. So these are the pairs of cofunctions. And this idea of them coming out the same, when you have cofunctions, that's called the Complementary Angle Theorem. Very simple theorem that just says if you have cofunctions of complementary angles, they're equal. Okay? But to have that theorem work, you have to meet two conditions. First of all, you have to have cofunctions. And second of all, you have to have angles that are complementary to each other. So instead of looking at an example with letters, let me show you one with numbers. Let me make one up. Sine of 10. I want to figure out what that's the same as. Not necessarily a decimal. I just want to know what it would be the same as. What's the cofunction for sine? Yep. Cosine. What angle is complementary to 10? Yep.
80 degrees.
80 degrees. Those two things are exactly the same. Let's try it. Sine of 10, you get that number, whatever it is. Cosine of 80, you get the same number. Okay? But you have to have two things happen. Those have to be cofunctions, and those have to be complementary. And then they come out the same. So, let's finish up by looking at that one. Those two things that I just underlined, sine and cosine, what are they? Ethan?
Cofunctions.
They're cofunctions. All right, so we have cofunctions. What do 35 and 55 add up to? So we have cofunctions of angles that are complementary. So what do we know about this value compared to that value? Since they're cofunctions of angles that are complementary. Yeah,
They're going to be the same value.
they're the same value. I don't know what the value is, but I know the value in the red box is the same as the value in the green box. So what does that mean this problem would come up to? Yeah.
0.
0, exactly. Not really interested if you can figure out what the answer is. I'm more interested if you can figure out and explain why it's 0. And that's what we just went through. And that's it. Any questions on that? All right, so tomorrow we'll take a look at the homework, and then we'll do what we can in 6.5 part 2. If we don't finish, not a big deal. We'll finish on Thursday because there's no other lesson planned for Thursday. So most of the homework is on page 361. But there are 2 questions similar to the 2 we just did, or the 1 we just did on the board. I'd like you to try to simplify sine 40 divided by cosine 50 using the theorem I just taught you. And then this one is basically the same problem we just did on the board. But try that one.